I wanted to add to what you were saying, but the best way I know how to do that is appeal to Wheeler.
Hmm.
Taylor and Wheeler have a nice introductory book about uh, the theory of relativity. And this is one of the early pages in the book
Hmm.
um, that I think helps fill out a little bit what these space-time coincidences are.
Hmm.
Do you see the PDF on screen?
Yeah, I see. I see it.
Oh, so um, yeah, up here they say, well, time between events is relative. Relative to is the distance between events. Yet behind these differences, Einstein discerned unity, concepts and quantities on which everyone in the universe agrees. What concepts and quantities? And they have four listed here: events, wristwatch time, the path connecting events, and conservation laws. So for events, they say an explosion is an explosion, a birth is a birth. Whether it is the birth of your star or your own birth, everyone agrees that it happens.
Hmm.
And wristwatch time, this is the amount of time read on a wristwatch if you carry it from one event to another.
Right.
That's the
Yeah.
proper time. And that's an invariant. And that's the path connecting events. So if you draw a world line, every observer will agree you were at event A, you were at event B, you were at event C.
Hmm.
Even if the time and distance between the events varies from observer to observer, they will all agree you were at those events. And then finally, you have conservation of momentum, energy, and angular momentum. And they'll all agree that those laws are obeyed in their own frames. In one frame, you might assign one value to momentum. In a different frame, you might assign a different value for momentum. But they'll both agree that in their own frames, the total momentum is conserved. Um, I think this is a nice intuitive way of spelling out
Yeah. Yeah.
what Einstein means.
Yeah. I agree. Yeah. Yeah. And I mean, some of these issues, like proper time, are issues that we're going to, I guess, go further into later with more detail. But yeah, I think that yeah, I found it. I actually found it really interesting with the discussion of overlapping events or connecting events and coincidences, because it, as you know, I wrote this paper on Russell's philosophy of science, and one of the major components of philosophy of science is his space-time theory and his discussion of the notion of punctuality to understand to give his like a structural account of science. And one of the major assumptions behind the notion of copunctuality is just this idea of coincidence. So copunctual events are going to be coinciding events in a four-dimensional spacetime. That's why he calls it copunctuality, because it's like this generalized idea of overlap. But I guess I didn't realize how close were the thinking of many of the philosophers working at the time. So because he mentions people like Einstein, but also people like Schlick, and now there's also like the Russell discussion, which Russell is, I mean, for me, it's an interesting case because he was having a discussion on conventionalism versus realism, but his discussion was against Whitehead. He was discussing with Whitehead, who was also interested in gravity and geometry, and with Eddington. So he doesn't quote Schlick or Reichenbach at all. This is in 1927, but he's still having that same discussion. So I mean, I guess for me, it's also like the not only the interest in itself of the discussion, but also the historical understanding it gives me of the sort of intellectual environment people were thinking about these issues.
Mm. Yeah, it's striking to hear that those discussions are going on in parallel.
Yeah.
Tells you something about the landscape that people, the intellectual landscape that people were working in. And that passage from Einstein, I think, gives a lot of force, if that's the word, to this observational theoretical distinction.
Yeah.
Because you can already see there's the observational stuff, the space-time coincidences, and then there's the theoretical constructions, like coordinate systems.
Right.
And the positivists understood that those coordinate systems, you have a very large degree of freedom in choosing them. And I think that motivates the conventionalist story.
Right. Yeah.
Um,
Yeah. I think we next time we meet, we're going to go more in depth into the objections to the conventionalist story that Friedman discusses, and also the part of the space-time, the part of chapter 2. But I was wondering, you had like any like closing thoughts before we finish this recording?
I guess just as a closing thought, I wanted to echo what Friedman says about the observational theory distinction early on, because of course there's a lot of understanding about the theory latedness of observation and how difficult, when you look closely at any observation, how theory is involved. And Friedman thinks we should not dismiss the logical positivists. And I think in that passage from Einstein, you can see some very strong motivations for pursuing it and giving
Yeah.
the positivists their fair shake, which is one of the points Friedman's trying to make.
Yeah. Yeah. One thing, I mean, I guess part of the stuff that I want to say as a closing thought is that I find myself interested in the distinction between coordinate systems, you know, the way in which they come together to give us a space-time theory, which is useful for actual science, is we do need the coordinate systems to actually make some applications, right? But then we think of the coordinate systems still as an artifact of the theory. I mean, when we look at general relativity, one of the things that we're going to be looking at is what the way in which you do coordinate systems there is peculiar, because you do it like you get like these coordinate systems that you patch together from different, you know, local coordinate systems. You put them all together. So I guess I'm interested in the way in which coordinate systems work in general, and their relevance for our own understanding. Even if they are part of artifacts of the theory, that doesn't mean that they are not incredibly important for science. So I want to find out more about their importance. I want to find out more about the connection between deep geometrical structures, for example, the affine structures. You know, we mentioned the flat affine structure of Newtonian spacetime, which distinguishes, you know, straight from curved trajectories, but we didn't get into the general relativity stuff where he discusses what he calls a curved affine structure. So you're still going to have a affine structure; it's just not going to be the same as in the Newtonian case. So I want to talk about these deep geometrical structures, the topology, the metric, the affine structure, but also in connection to something that Friedman mentions briefly, but doesn't discuss at length here, which is group theory, right? So the what he calls the Lorentz group, for example, or the Galilean group. And this had to do with the sort of admissible transformations. So I guess but this is something which I am, as a philosopher who's interested in space, I mean, still trying to get my mind around with. So I'm going to try to ask Tim some questions on this and see if we can together get some deeper understanding on some of these ideas. So, I mean, obviously, you know, the main methodological point for me to keep thinking about is just what we mentioned earlier about good theoretical terms versus bad theoretical terms, and what they say about what the world is like. But I think that this question is inextricably linked to the questions about our representations are mathematical representations of the world in science. And what do we mean when we say that some of them are artifacts and some of them um, are more substantive? What does that mean? I don't think that that's clear. I don't think that people have enough clarity about that even today. So yeah. So I guess I'll close this today. Thanks, Tim, for joining me.
Yeah, it's been a pleasure. I'm looking forward to pursuing the agenda you just laid out.
Yeah.